Thank you so much. Before I make a introduction, maybe let's do a turn on video camera first, and then we want to take a photo for memory. So please turn on video camera.好。
好。
So, will you take a photo?
Yep, already, Professor. Maybe we're waiting one more second, please.
Okay.
Yeah, maybe I took the group photo now. Thank you so much already. Thank you, Professor. Thank you, Professor. I have finished already.
Okay.
Okay, we can start.
Good afternoon, the distinguished guest from DUT and a colleague and a student from NCKU. Welcome to participate in webinar of NCKU and the Vinh research project on the topic of a novel three-pole DC to DC converter for sustainable energy system. I'm the project principal investigator, Professor Tsorng-Juu Peter Liang from National Cheng-Kung University. And the project principal investigator is Associate Professor Vinh. Is also the rector of the University of Danang, University of Science and Technology of Vietnam. And on behalf of the PI of this project, I'm very pleased to introduce the presenter, Peter Quang. Huang Jin Jianye Peter Quang was born in Ho Chi Minh City, Vietnam in 1996. He received his bachelor and master degrees in EE from National Cheng-Kung University in 2018 and 2020, respectively. He is currently pursuing his PhD degree in EE in NCKU. His research interests include power converter technology, topology, and the converter for sustainable energy system. So, ladies and gentlemen, please join me to welcome Peter Huang.
Thank you very much for your introduction. Good afternoon, everyone. My name is Peter Huang, and I'm from National Cheng-Kung University. Today, the topic of my presentation is Introduction and Applications of Three-Pole Converter. Okay, this is the outline of my presentations. First, I'm going to make a brief introductions about three-pole converter, include its background and motivation. Then I will make a short operating principle analysis. After that, the design considerations of some important components are discussed. And then I will show the experimental result to verify the theoretical analysis, and finally I will make a brief conclusions about the proposed three-pole converter. And let's go into introduction. First, I'm going to talk about the background and motivations. Because environmental problems have become global issues, so renewable energies become essential to energy solution in recent years. The solar power and hydrogen power have been very well developed for very applications, we can see in this figure it has been implemented into the source of the unidirectional DC to DC converter to transfer energy to load. However, the output voltage of the solar power and hydrogen power system are low. So in order to provide continuous energy to load, the renewable energy require a battery backup as an interface among the energy source. So this is combinations of the unidirectional DC to DC converter and bidirectional DC to DC converter in order to transfer energy to load. So we can see that traditionally, multiple DC to DC converter are adopted to transfer energy to load. However, in the recent year, in order to reduce the numbers of converters, the integration of multiple converters into a single module, namely the three-pole converter here, is illustrated in the figure below. It has many advantages, include the fewer power conversion stage, the lower number of components, and lower overall volume. It also may have higher power density. There are mainly two types of three-pole converter, which are the isolated three-pole converter here, which usually the battery and main source have the same grounding, but they will have separate grounding with the load, and the non-isolated three-pole converter, which all three poles share the same ground. The isolated three-pole converter have the advantages of the electrical isolation, and usually it can achieve zero voltage switching and fits for different voltage level because the voltage level can be adjusted by the transformer. However, it usually require more components and require the isolated control and have to solve the leakage inductance problem of the transformer. The non-isolated three-pole converter will have the simple circuit structure, simple control methods, and the all poles share a common ground, but it may suffer from the low energy conversion ratio. So in order to solve the problem, the proposed three-pole converter, which have a step-down non-isolated conversion, it shows in this figure, is essential for the low voltage applications. This high step-down three-pole converter is constructed by a tapped-inductor structure and is combined with a buck converter. It can be achieved a high step-down conversion ratio and also the independent power flow among poles from the main source to auxiliary battery, from auxiliary battery to load, and from main source to load. These are the 5 operating strategies which will be analyzed, which are the single input, single output. Number 1, which I call it CISO 1 stage, where the energy will transfer from the main source to load. Another operating strategy is CISO 2 stage, where the energy will transfer from battery to load. In the CISO 3, energy transfer from the main source to the battery, and the dual input, single output, the DSO state, the energy from both the source and battery to load. And finally, it is single output, dual output, where the energy from the main source will transfer to load and battery. Okay, now I'm going to talk about the operating principle. But before that, I'm going to make some assumption. The converter is operated in the steady state under the CCM control. all components are considered the ideal device. The turn ratio of the coupled inductor are defined as the NP over NS and is equal to N over 1. The capacitance of the CO and CS are large enough so that the VO and VCS can be considered as constant. Okay. Let's talk about the operating principle of CSO 1, which the energy from source will transfer to load. This mode usually happens when the battery is cut off from the three-pole converter, so only the energy transfer from VB1 to VO. The control trajectory is to control the switch S3 and S4 duty and let the VGS1 and VGS2 equal to 0. In mode 1, from T equal T0 to T1, the switch S3 is on, and at this time the ILK, the leakage inductance is smaller than ILM, and the ILK and ILM will increase linearly, so the VB1 and CS transfer energy to the LM and load. This mode ends when the ICS, the energy from CS release to 0 at T equal to T1. In mode 2, VGS3 is still high, but ILK is now smaller than ILM, and ILK and ILM increase linearly. The VB1 will release energy to the LM and load. This mode ends when VGS3 become low at T equal to T2. In mode 3, VGS3 and VGS4 are low, so the anti-parallel diode of the switch S4 will turn on. The ILK and IL smaller than ILM, and ILK and ILM decrease linearly. The energy from LK will lead to CS. This mode ends when the switch VGS4 become high at T equal to T3. In mode 4, from T3 to T4, the VGS4 is high and the ILM is smaller than ILK. The LK energy continue to relate to CS until the leakage inductance relate to 0 at T equal to T4. In mode 5, the VGS4 is high and ILM decrease linearly. The ILM transfer energy to load through the coupled inductor, and this mode ends when the VGS4 become low at T equal to T5. In mode 6, when VGS3 and VGS4 are low, ILM continue to decrease. LM transfer energy to low through the coupled inductor, and this mode ends when the VGS3 is high at T equal to T6. Okay, the next mode is the CSO2 mode, when the energy from the battery transfer to load. This mode usually happens at the night time when your PV panel have no energy, so only the battery transfer energy to load. And the control trajectories is we control the switch S2 here, and let VGS1 and VGS3 equal to 0. So it will operating like a traditional buck converter. When the VGS2 is high, the VB2 will transfer energy to the LM through coupled inductor and to load. This mode ends when the VGS2 equal to 0 at T equal to T1. In mode 2, VGS2 and VGS4 are low. The anti-parallel diodes of S4 turn on. The LM will transfer energy to load. This mode ends when the VGS4 is high at T equal to T2. in mode 3, the VGS4 is high and LM continue to release energy to load. This mode ends when the VGS4 is low at T equal to T3. And when VGS3 and VGS4 are low, LM continue to release energy to load through the coupled inductor. This mode ends when VGS2 is high at T equal to T4. The next operating mode is the SISO3 mode, when the main power source will transfer energy to battery. This mode usually happens when at the very light load conditions. So when it's also operating like the buck converters, traditional buck converter. So when VGS1 is high, energy from VB1, but the main source will transfer to the battery. This mode ends when the VGS1 is low at T equal to T1. And when the VGS1 is low, the inductor LA will release energy to VB2. This mode ends when the VGS1 is high at T equal to T2. So both SISO2 and SISO3 are the traditional buck converter operating mode. The next operating mode is the diesel mode, when energy from both the main source and battery will transfer to load. This mode usually happens when during the heavy load condition, so it will require both energy from source and battery. The control principle is we control the switch S2 and S3 duty and let VGS1 equal to 0. When VGS3 is high, the ILK is smaller than ILM, and both ILK and ILM will increase linearly. So the energy from the VB1 and CS will transfer to the LM and load. This mode ended when the ILK here equal to the secondary side current, which means the ICS equal to 0 at T equal to T1. In the second mode, VGS3 is still high, ILK smaller than ILM, and ILM increase linearly. The energy from VB1 continue to transfer to LM and load. This mode ends when the VGS2 become high at T equal to T2. In mode 3, VGS3 and VGS2 are high. The ILK is smaller than ILM, and ILM will increase linearly. The VB1 will continue to transfer energy to LM and load. Although VGS2 is high, but the VB battery voltage usually lower than the main source power. So in this mode, the VB2, the energy from battery still cannot transfer to load. And this mode will end when VGS3 is low at T equal to T3. In mode 4, now VGS3 is turned off, VGS2 is high, so the energy from the battery will transfer to LM to coupled inductor and to load. Now the leakage inductance LK will release energy to CS. This mode ends when the ILK equal to 0 at T equal to T4. In mode 5, the VGS2 is high. The VB1 continue to release energy to LM and load. This mode will end when the VGS2 become low at T equal to T5. In mode 6, the VGS2 and VGS4 are low. The LM now will transfer energy to load through the coupled inductor, so the anti-parallel diode of switch S4 will turn on. This mode ends when the VGS4 is high at T equal to T6. In mode 7, the VGS4 is high. The LM transfer energy to load, and this mode will end when the VGS4 become low at T equal to T7. In mode 8, VGS4 and VGS2 are low. The LM continue to transfer energy to load. This mode ends when the VGS3 is high at T equal to T8. And the final operating mode is the CDO mode, when the energy, the main source power will transfer to the load and battery. This mode happens when the during daytime, and your main power source from PV will have very large power, so it can transfer energy to both battery and load. The control principle is that we can control the switch S1 and S3 duty and let VGS2 equal to 0. In mode 1, when VGS3 is high, ILK smaller than ILM, and ILK and ILM will increase linearly. The VB1 and CS will transfer energy to the LM and load. The energy from the inductance LA will transfer energy to battery. This mode will end when the current ICS equal to 0 at T equal to T1. At mode 2, when VGS3 is high, the ILK is smaller than ILM. ILK and ILM increase linearly. The VP1 will transfer energy to the LM and load. The LA continues to transfer energy to VP2. This mode ends when the VGS3 is low at T equal to T2. In mode 3, VGS1, VGS3, VGS4 are load. The LM will transfer energy to load to the coupled inductor, so the anti-parallel diode of switch S4 will turn on. The LK will release energy to CS, and the LA continue to release energy to battery. This mode ends when the VGS1 and VGS4 are high at T equal to T3. In mode 4, VGS1 and VGS4 are high. The LM will transfer energy to load. The LK will transfer energy to CS. And now, because the switch S1 turn on, so energy from the source will transfer to battery. This mode ends when the energy from the LK transfer to CS equal to 0 at T equal to T4. In mode 5, both VGS1 and VGS4 are high. LM will transfer energy to load through the coupled inductor, and the energy from source will transfer to the LA and battery. This mode ends when VGS1 equal to 0 at T equal to T5. In mode 6, the VGS4 is high, so the LM continue to transfer energy to load through coupled inductor, and the LA transfer energy to battery. This mode ends when VGS4 equal to 0 at T equal to T6. In mode 7, VGS 1, VGS3, VGS4 are load, and LM transfer energy to load through couple inductor, and the LA transfer energy to battery. This mod M when the VGS3 become high at T equal to T7. Okay, let's go into the design considerations. This table shows the system specifications of the Ropost converter. The main energy source is the 300 volt. The battery is 48 volt. The output voltage is 24 volt. The maximum power is 300 watts, and the switching frequency is 50 kilohertz. So first, we have to define the voltage gain of the CISO1 stage. It's a tapped inductor, so when switch S3 on, the voltage on the magnetizing inductance LM VOM will be equal to N times VB1 minus VO over N plus 1. And when the switch off, the voltage is equal to N times VO. So by the 1-second balance of the LMs, we can define the VO over VB1 is this equation. In the CISO2, it's just the traditional buck converter and controlled by the H2 duty. So by the 1-second balance of the LMs, we can define the voltage gain of battery to load. Very similar to the CISO2 mode. The CISO3 mode is also the traditional buck converter. So by 1-second balance of principle of the inductor LA, we can derive the voltage gain between the battery and main source is D1, which is the duty cycle of switch S1. The diesel gain will be a little bit different. When switch S3 on, the voltage on the switch, on the inductance LM equal to N times VB1 minus VO over N plus 1. And when switch S2 on, the VOM will be equal to N times VB2 minus VO. And when switch S4 on, the VOM will equal to minus NVO. So by the 1-second balance of the inductance LM for the 3-time period, we can define the voltage gain of VO. Is have the relationship with both the main source and battery, and the duty cycle of switch S2 and S3. The CISO gain can be easily derived by the mod CISO1 and CISO3, because the CISO is the combinations of mod CISO1 and CISO3. Therefore, the voltage gain of the CISO, where the relationship of main source and VO can be derived same as CISO1, and the relationship between the battery and source is same as the CISO3. Next, we have to decide the turn ratio. This figure shows the voltage gain of the CISO1 versus the duty cycle of D3. And you can see that when the D3 range from 0.25 to 0.5, the turn ratio range is from 3 to 10. So the suitable range for a step-down converter is usually from 0.25 to 0.5. So the turn ratio we have to choose is from 3 to 10. So let's keep it in mind for now. When the switch S3 is on, the CS will release energy to VO, and the IOK also increase linearly. Now we can see that the VCS in the short time will equal to the VNS plus VO, which equal to these equations. And when the switch S3 turn off, the IOK will release energy to CS. And the VCS charging time will equal to N time VO. So the clamping voltage of switch S3 can be derived by VB1 plus VCS, which equal to the VB1 plus NVO. For the limitations of these clamping circuits, in order for it to work in steady state, the charging current voltage you have to be smaller than the discharge current voltage. So the condition for these clamping circuits can be derived by this equation. N will be smaller than the VB1 over VO, so it's be smaller than 3.53. So the N equal to 3 is chosen. For the inductance LM design, I set the PCM conditions of IO and IP2 at 20% rated load. So we can calculate the inductance LA and LMs in the PCM conditions by D2 equation. Next, I will show the experimental results. This table shows the key parameter and components. The high size most switch is the IPA 65R190C7. The switch S2 and S4 have the same key parameter, and the clamping capacitance is 4.7 microfarad, and the turn ratio design is equal to 3. This is the prototype of the Ropo converter. It has the size of 20 times 15 times 5 centimeters, and can see that this is the source port, the high voltage port here, and this is the battery port, and this is the low port, and this is the magnetizing inductance LM, and this is the inductor LA, and this one is the clamping capacitor CS. This figure shows the waveform of CISO1 mode when Vin equal to 300 volt, VO to 24 volt at 50% load. And this is the waveform of the CISO1 full load conditions when V equal to 300 volt, VO is 24 volt. And this figure shows the measure efficiency curve of the CISO1 mode from 10% load to 100% load. The high efficiency is the 50% load, which is 94.3%, and at the full load conditions, the efficiency 91.2%. And this figure shows the apparent waveform of Tsorng-Juu mode when Vin equal to 300 volt, and this one must Vin equal to 48 volt and VO equal to 24 volt, and the is at 50% load. And this is the full load conditions when energy transfer from battery to load. And this figure shows the efficiency curve of Tsorng-Juu. The higher efficiency is 97.1% at 20% load, and the heavy full load efficiency is 95.7%. And in the Tsorng-Juu mode, when we transfer energy to battery, and this figure shows the 50% load conditions. And this one shows the full load condition. This is the efficiency curve of the Tsorng-Juu mode. The highest efficiencies happen as the 60% load, which is 94.4%, and the full load efficiency is 93.7%. The next one is the diesel mode at the 50% load conditions. This one is the diesel mode waveform at the full load condition. This is the efficiency curve of the diesel mode. The high efficiency happen at the very light load conditions, which is 95.1%, and the full load efficiency is 90.5%. This figure shows the waveform of the Tsorng-Juu mode in the 50% load conditions when and the battery power is also at the 50% load conditions. This one shows the waveform when load power is full load and the battery power is 48 watt. And this figure shows the waveform of Tsorng-Juu mode when battery power is 50% and the load power is 48 watt. And this one shows when the battery power is full load and the VO power is 48 watt. The Tsorng-Juu, this is the efficiency curve of the Tsorng-Juu mode. Of the first one is the when the low power changing from 10% to 100%, and the next one is when the battery power change from 10% to 100%. The high efficiency is 95% at the 60% load conditions. And finally, I will make a brief conclusions. The three-pole converters with the high voltage gain is proposed. It have the simple structure and fewer power electronic device with the simple control methods. the high efficiency is 97.1 at 20% low in the CSO2, and also the power flow from the 3 poles are independent. And thank you for your attention, and I'm open for questions.
Peter,
Yes.
we receive 2 equations from chat. You can look at the question.
Okay. Okay, the first questions is said that what is the most difficult when you create the 3-pole converter? Okay, I think the most difficult thing when create the 3-pole converters is the power flow, because in the traditional DC to DC converter, we usually only have the energy transfer from V in to VO. But when we create the 3-pole converter, we have one more pole, is the battery pole. So we have to consider, like when the V in transfer energy to VO, is there any effect of the energy from battery? Yeah, it's the power flow. I think it's the power flow.
I believe a topology, how to create the topology, that's also challenging too, right?
Yes, it's very challenging. Also, the price of the transfer function, how to verify your transfer function is correct or not.
Okay. And the second.
The second question is, in case lack of sunlight and insufficient or unstable power from the battery, what will happen? Do you have any solutions for the problem if it's happened? So because this is a 3-pole converter, so when the lack of sunlight, which means that the main power source have low power, so most of the energy transfers will come from the battery. So we can use the CSO2 mode when all the energy power will transfer from battery to load, or we can use the diesel mode, which control the switch S2 and S3. The switch S2 will control the battery power, so we will use more battery power to provide energy to load and less energy from the PV source, which controlled by S3. So I will increase the switch S2 duty and decrease the switch S3 duty.
Well, under a specific condition that the sunlight and battery power are lower than requested load power. Under this critical condition, we have to reduce the power supply to the load. Okay. And then we have a third question.
Okay. The first question is, how much is the output voltage? Is it adjusted or can supply to high voltage equipment? Okay. Because I think the output voltage is adjustable, but this is because this is the low voltage application. So if we want to apply to the high voltage, maybe I had to change the DC to DC converter structure, because this is a step down. So I think it can go up to 20 kilovolt.
Okay, I made some additional comment. First, the load of 24 volt is usually for accessory power application. The second is if for plasma over 20 kilovolt application, we need to use isolated power supply because of a safety issue. Okay. So, any more?
Yeah, there's one more question. It said that what is the highest voltage that the 3-pole converter can generate? Is it stable I think the output voltage, of course, is will be stable because it's good controlled by the DC to DC converter, and the high voltage that the triple converter can be generated because it's a step down converter. So I think the high voltage it can be generated is about near the input voltage, because the input voltage is a 300 volt. So if I use the same DC to DC converter, the high voltage, the output port can be achieved is also 300 volt at most, but it will be lower. But of course, the output voltage will be stable.
Okay, thank you. So any more comment or suggestion for Peter?
Okay, I've heard that you have research only on steady state, all right? And but we know that during operation, the mode can change from one to another mode. For example, when the load grow up, so the energy we can take not only from the PV but also from battery.
Yes.
Or the power from the PV grow up, so energy can come from PV not only to the load but only supply for the battery. So how about the transient state in this case? Have you got any research on that? When the mode transform from this one to another one.
Peter, you can try.
Okay. Okay, first, so because the changing power, so first if I have to do it, so I have to detect the output power change. So let's see.
Yes. No, when the
for example, usually when output power increase, the mode will change from the CSO 1 to the DSO. The CSO 1 is energy from the main source to the load, and the DSO is from the both battery and PV power to load. So when I detect the change in the output port, because the low power increase, and first the VO will decrease. So I will detect the trend of voltage. If VO drop too much, I will open the switch S2 for the battery to provide energy to load. Yes, because the energy from battery is controlled by the switch S2.
So we should try that.
Yeah, I should try that.
Yeah, I think I can make some additional comment. Actually, the transient response for the DC, like a DC small grid system, will be much faster than the AC grid system because of DC sources and DC load. So it is easy to detect input source and output load condition. Okay, so any more comment? Peter, there's one more question. How to apply this research result in Vietnam?
Well, well, trick question.
In Taiwan also, because now we know that the PV on-grid system is popular now, but the system it should be in the off-grid system. So where we can apply the three-porter convector now.
I think as I mentioned after Peter's presentation, the three-port converter with high step-down conversion ratio is much suitable for providing auxiliary power to load, not to the main load. But if the three-port converter with high step-up, in which the bus voltage is around 380 or 400 volt, would be much suitable for like a home house or standalone application. So that's a different scenario. Okay. And then we still have some more time. I think I can make some short comment about Peter's presentation. Peter, would you move to page 33?
Okay. $33.
Yeah. Just one comment is actually we can use replace S4 with a diode, but the reason we use a switch is a function as a synchronous rectify to improve the system efficiency. So that's not the S4 is not mainly for switching. It's mainly for synchronous rectify for improving the system efficiency. The second is I think that's the future work for Peter's research. We can try to integrate LA with coupled inductor together, so the overall system both sides will become much complicated. Okay, this is my additional two comments. So any more comment or question from audience? Okay, and then thank you so much for the great speech by Peter Huang. And then thank you so much for you participated in this webinar. Thank you.
Thank you very much.
Thank you.
Kien and
Hope to see you soon.
Bye-bye. See you
Hope
later.
to visit you soon. Okay.
Okay, bye-bye.
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 Thank you very much.
Bye-bye.
From Hayden.